Okay, we're tackling endo and exothermic reactions. So these are just terms to tell whether or not we have had a net absorption of energy or a net release of energy through having a chemical reaction. And so that also involves whether or not we're forming more bonds than breaking, or if we're breaking more bonds than forming. So, what I've done to kind of simplify all that is I've drawn a picture. So, here we have two people that are linking arms in the middle. So, these guys in the middle are linked. And then we have two people that are on the other side. This one's got a broken leg. That are trying to pull these two people in the middle apart. So it's like taking a tug of war, but instead of using a rope, the tug of war has two people with their arms linked. And so the bottom line is that if you're trying to break these two people apart, it's going to take a lot of energy to separate their arms from each other. And that's how it works in chemistry. So when you're trying to break a bond like that, you are going to have to expend or take in a lot of energy in order to break that bond. So what does that mean? Well, in this case, we're going to write ourselves a little note that reminds us that it takes energy. So I'm going to write take energy to break. And by breaking, we are breaking chemical bonds. And so in this case, how I can remember this is if I'm taking in energy or absorbing, I'm going to break something. So take to break, and that helps because they rhyme. But remember that by saying take, we mean that we are having more absorption of energy. And then this type of reaction, since we're taking more energy in to break bonds apart, is called an endothermic reaction. So I'm going to write endo for short. Now if we go to the other side, I've drawn another picture. And this picture over here on the right has a different scenario. We have two people that are already apart, but we have two people on the very outside. And instead of trying to pull two people apart, they're actually trying to push two people into each other in order to form a bond. And the way you can picture this is you can see that the person that's waiting to be pushed is leaning backward a little bit. And by leaning backward, they are kind of a weight or a burden to get rid of. And so it's this huge release when we push them forward and get rid of them. And so in this case, we are releasing energy in order to make a bond form or to get these two people to come together in the middle. And so what we're going to write up top here is release energy to form a bond. So we're going to highlight release to form. And so we have release to form and take to break. And if we're releasing energy to form more bonds than break, so this is going to then be called an exothermic reaction. So the bottom line is, if you're releasing a bunch of energy through a reaction, that means you formed more bonds than you've broken, and that is an exothermic reaction. But on the other hand, if throughout the chemical reaction, if you have absorbed energy, that means that you have absorbed energy in order to break more bonds than form. And so that would then be called an endothermic reaction. So anyway, the bottom line is that endo and exothermic reactions have certain qualities to them that we can experience through labs. So in this case, here's some signs of exo and endothermic reactions. If you are feeling heat, if it feels hot to the touch, or if you see light like fire, if you hear a sound, you're most likely looking at an exothermic reaction because all three of these examples are signs of energy being released, which means bonds were broken. But if we go, bonds were formed. But if we go on the other hand, and if you need heat to make a reaction happen, if you have to put heat energy in to cause a reaction, or if you have to have light to start a chemical reaction, or if it feels cold to the touch, you're looking at an endothermic reaction, which means that we are absorbing energy in order to break bonds. So exo, we're releasing energy in order to form bonds, and then endo, we are absorbing energy in order to break them. So here, let's look at our clues to see which one's exo and which one's endo. When two chemicals mix, their temperature rises. That means we're heating up, so this is going to be exo. A solid burns brightly, and we don't even need to read anything else. If we're burning and releasing heat, light, and sound, that's going to be exo. As two chemicals are mixed together, the temperature drops. So we're getting cooler, so this is going to feel cold, not hot, so this is going to be endo. And then if we have two chemicals that will only react if you heat them continually, that means we have to put in energy in the form of heat to cause a reaction to happen. So this is going to be endo. And if we are taking in light energy or absorbing energy, this is also going to be endo. Now, what does this look like on a molecular level? So in this case, we have a picture, and we have a compound, copper carbonate, CuCO3, being separated into two pieces. So we have copper oxide, and then we have carbon dioxide. And so what we're going to look at is, just by looking at this on a basic level, we can see that our copper atom, which is represented here, and one of our oxygen atoms are separated off from the carbon and the other two oxygens. So basically, long story short, we've broken one thing into two pieces, which means that we have broken bonds. By breaking bonds, we have had to take in energy. So by taking energy in order to break them, this is going to be classified as an endothermic reaction. But now what we're going to do is, this is going to be very, very tricky. We're actually going to represent these molecules as Lewis dot structures. So to start, we have copper. I'm going to zoom out a little bit. Copper will have two valence electrons that it will have given. This is a copper ion, so it's going to have a charge of 2+. Then we're going to do the rest of the atom. Carbon is going to have a double bond to oxygen. Then it's going to have two single bonds to the other oxygens. This, which is going to be a little bit tricky, is going to cause each oxygen to have a charge of 1-, and let me talk about why. If I include the dots on our bonds at each end, we're going to see how many electrons each atom has access to. So if I focus on this carbon has 4 electrons around it, which is its number of valence electrons. Then it has access to 2 over here, and then 1 over here, and then 1 over here. 4 plus 4 that it has access to is a total of 8. So carbon, having access to 8 electrons, is stable. But now if we go back, let's check out our other atoms. And our other atoms would be oxygens. Well, if we look at the double bonded one, this has 6 around it, which makes it stable because it has 6 in its Lewis structure, but it has access to 2 more to get it up to 8, so it's stable. But if we look at the other two, they want to have normally 6 electrons immediately surrounding the atom. But if we look at our dots, we have 7 immediately surrounding each oxygen. But it has bonded to 1 on each side. And so in this case, it has access to 8, but because it's surrounded immediately by 7 dots instead of 6, this is going to give it a charge of -1. We're going to do the same one to this one since it's bonded in exactly the same way. And if we look at this, our 2 -1s equal a total net charge of this side of the molecule as -2. And -2 is a perfect balance for the 2 positive. So what we have is a combination of an ionic bond here, and then we also have a covalent bond among the carbon and the oxygen bonds. So that's kind of tricky. Now what we're going to do is we're going to break this apart. So if we draw a little arrow to show that the reaction is happening, what's going to happen is copper is going to chill out here. But what's going to happen is, since this is an endothermic reaction, we're going to break a bond. Here's how this will work. Oxygen on the bottom, so what I'm going to do is actually copy this. Oxygen on the bottom is a more electronegative atom. It also, in its normal state, has an even number of valence electrons. Because of these two facts, it is going to actually take the bond from itself in the carbon and take it for its own. And so what happens is this carbon is going to lose this bond. So this guy is going to come off, and then we're going to get rid of that line there. And so now our oxygen has a total of 8 valence electrons, which it did before, but now it normally would have 6, but it's got 8 dots immediately surrounding it. So even though it's got those 8 electrons at once, it now has a different charge than -1. Because it normally has 6, but now it has 8 dots immediately around it. This means that it has a -2 charge. Who's it going to want to bond to? Or copper. These guys are magnetically or ionically attracted to each other, and so they separate and they form their own compound. That's step 1. The next step that is really complex is what's going to happen here. Well, because the oxygen, again, has normally 6 valence electrons and 8 total electrons, which are even numbers, it has the ability to change this setup that we have between the carbon and the oxygen up top. So what do I mean by that? Let's check out carbon first. Carbon has 1, 2, 3, 4, 5, 6 electrons that it has access to. But it wants access to 8 to be stable, and so what this means is that it's going to now have a +2 charge. The problem is a +2 and a -1 do not stabilize. This makes an unstable compound. So what we're going to do is oxygen being more electronegative and having an even number of electrons has the ability to actually donate an electron, actually donate 2 electrons to itself and carbon. And so what I mean by that is we're going to take this guy, move him down here, and this can form a double bond. Now, don't get too caught up on the fact that that happened. These are advanced rules for upper level chemistry, but that's just a brief explanation of the why. And why did that happen in the first place? Because it wasn't stable. The +2 and the -1 did not balance out. And so if we look at this, let's kind of take a step back here. Well, let's check our new charges. Oxygen has 1, 2, 3, 4, 5, 6 electrons now surrounding it, which is what it likes. But it also has bonds to 2 extra ones. This means that it has no charge. Carbon has 4 valence electrons immediately surrounding it. 1, 2, 3, 4. That's what it likes, but it's still bonded to 4 more to get up to 8, which means that it is also stable. So that means that this has no charge anymore. And so if we look at this, we're seeing that we have fixed our problem and that we've now made a stable product of carbon dioxide. And so that's how that actually happened. We broke the bottom oxygen from the carbonate here, and then what we did was we bonded it with the copper, and then what happened here was the oxygen was able to donate a pair of its electrons up top to the carbon, and then we were able to make a double bond. Now for number 4, we're going to kind of go simpler. So the gist is you're going to see what's called a coefficient here. The coefficient means how many H to H bonds we have. So H2 looks like that with our 2 valence electrons. Since there's 2 of them, I'm going to have H to H, and I'm going to do it again. Now for O2, what's going to happen is I'm just going to do the same thing. So what we're going to do now is take a minute to draw in the rest of your molecules / compounds, and then we're going to look to see if this was a physical or a chemical change. So we do O2, double bond. Taking a shortcut here, not drawing all the dots. And then we zoom out, and let's take a look at this. H is bonded to itself over here, and so is the oxygen. Do we have the H bonded to itself on the right side of the arrow? No, it's bonded to an oxygen. Okay. What we're seeing here is that we have a new type of bond. But if you look at it, we have the same number of each element on either side. We have 4 hydrogens on this side, 4 over here, 2 oxygens on this side, and 2 over here. So even though we have the same number of atoms, we have a different arrangement, which means that this was a chemical change. Okay, now we get down to here. So this part is a little bit tricky. So what we're going to do is draw in our Lewis structures, but we're not going to do the dots just to save some time and effort. So CH4, if we look at our key here, carbon is the large black one, hydrogens are the small white ones, and oxygen is the large gray. So this means that this is CH. These are all going to be single bonds if we were to take our time and do Lewis structures. Then we see oxygens. So these are going to be oxygens. When oxygen binds to itself, it has a double bond. And then we're going to go over to the other side. Then we have carbon dioxide. These are going to be double bonds between the carbon and the oxygen. And then our final one is H2O, which is oxygen in the middle with 2 single bonds to hydrogen. Now the easy thing is we just have to count how many of each type of bond we have. So on the left side of the arrow, we need to count how many carbon and hydrogen bonds we have. We have 4 single bonds, so that means that we're going to have 4. Now for oxygen, these are double bonds. We're still going to count them as one type of bond. So this is one bond, and that is one bond. So if we look at this, we have 2 oxygen to oxygen bonds. Then we go to the other side. How many carbon and oxygen bonds? Same principle, 2. How many bonds between hydrogen and oxygen? 1, 2, 3, and 4. So let's count our bonds. We have a problem. 4 plus 2 equals 6, total bonds broken. And 4 plus 2 equals 6, total bonds formed. We can't tell between this amount of information if we've broken more bonds than formed, so we can't conclude whether this is an exothermic or endothermic reaction. So we write, no, we don't know yet, based on the bond counts alone. We can figure this out, however, and we have to do a final step. So all we got to do is look at another statistic, and what we check out is that if we look at the different types of bonds, carbon to hydrogen bond, oxygen to oxygen, and so forth, they have different strength values, and this is called enthalpy. It just means how strong the bond between the 2 atoms is. The higher the enthalpy, the stronger the bond. Carbon dioxide bond would be our strongest bond on this chart. So all we got to do is figure out how much energy we have on each side to see whether or not more energy was taken in to break bonds or released to form bonds. So what we're going to do is just take our number of each type of bond, multiply it by the strength value, and then we'll weigh each side. There's 4 CH bonds according to our chart, so 4 times 413 is what we're going to have to compute. 2 times 395, and 2 times 799, and 4 times 463. These numbers came straight from our chart. So then I'm going to go down here and write it out. Here's our arrow. So I have 4 times 413 plus 2 times 395 for our oxygen to oxygen bonds. And we're going to go ahead and equal that out. 395 times 2 is going to be 790. And then 4 times 413 is going to be 1652. And then if we go over here to the right side, we're going to check out 2 times 799. It's going to be 1598. And we're going to add that to 4 times 463. 4 times 463 is going to be more than 3,000. Total. So that's going to be 1852 here. But if we add that to the 1598, that's going to give us a total of 3450. That, just by looking at this, is going to be higher than this side. 1652 plus 790 is going to be a total of 2442. So what does this mean? Our right side is higher, which means that our right side was the amount of bonds formed. And so if we had more energy in forming bonds than we did on the side where we absorbed energy in order to break bonds, then this means that because we have more energy that we released in order to form the bonds, we've released more energy through the reaction. That means that this is an exothermic reaction because this side is higher than the other. If it was reversed, then it would be an endo. Now, the final part of this is, what does this look like on a graph? Well, this is the easy part. So activation energy is our first term that we're going to label on this curve. And activation energy means how much energy does it take to make this thing happen. So we're going to write act E at the hump of the graph. And then you guys just learned functions in math. And so what this means is that our input side is going to be on the left. And that is called the reactants. We take two things and we react them together to create a reaction. And then what's produced at the end of the reaction is called product. So that's going to be on the right side. And then if we look at this, our energy, which is graphed here on the left side, that's our measurement, it's higher on which side of the activation energy hump? We have more energy over here, which means that through this reaction happening, we have increased our energy by absorbing energy throughout the reaction. Since energy is absorbed, this means that we have taken in energy in order to make a reaction happen. And so that is going to be an endothermic reaction. Remember, endo is take to break. Take in energy, break bonds, endothermic. But if you're doing an exothermic reaction, it's going to be the opposite. So you start out with a higher energy, and through the course of the reaction, you release energy and end up lower than what you began with. So this is our energy released. And a great way to remember this, okay, how do I remember all this stuff, is when you exercise, when you work out, your body heats up, so you sweat. And when you work out, you expend energy throughout the process. And so even though you feel really good after a workout, you have released energy. So you have less energy after the workout than you have begun with. And so what this means is that because you're hot through working out, you are experiencing an exothermic reaction. You are releasing energy through metabolism. And by doing that, you are heating your body up. And so a good way to remember that is when I work out, I get hot. And so that means I'm releasing energy because I'm tired after I'm done. And so this is an exothermic reaction. Hope that helps. And that's all we're doing for today.